So I'm going to start going over how you do these problems for related rates. First of all, we'll do page 2, class problem 1. This is the oil spilling from the ruptured tank. What we want to do is identify what geometric shape is involved in this problem, and this is a circle because it's a circular pattern, and it has radius, and the radius increases. So we look for keywords like increase, decrease, vary, change, at a constant rate, and rate means derivative of 5 feet per second, so we'll be entering that information later. So how fast is the area? How fast is the area is the question. They're asking for a dA dt, the derivative of the area. And when the radius of the spill is at 25 feet, that is the information that you put at the end. So the variables that we have are R for radius, A for area, and the rates of change, we have a rate of change of the area with respect to time, which is 5 feet per second. We also are asked about the rate of change of the area, so we'll call that dA dt, and that's what we don't know, that's what we're going to solve for. Draw a picture. The picture is very simple, it's just a circle which represents the oil spill, and it has a radius. And to relate radius and area of a circle, the area is equal to pi times the radius squared. The next thing we're going to do is differentiate that equation so with respect to time. So the derivative of A is just dA dt. Pi is a constant, so it would be pi times, bring the 2 down, 2r dr dt. And then the last thing we do is substitute everything that we know, including when the radius is at 25 feet way back in the beginning. So substituting the values in, we're trying to solve for dA dt. So dA dt is equal to pi times 2r is 25 from the beginning of the problem, times dr dt. You know what? Let's put 25 feet in here. Let's get our units in here. So 2 times 25 feet. And then the dr dt from the beginning is 5 feet per second. And when you multiply everything out, 2 times 25 is 50, or 2 times 5 is 10. 10 times 25 is 250. So our dA dt is equal to 250 times pi, and then we have feet times feet is square feet per second, and that is the end of that first problem. The second problem talks about the area of a square. So the geometric shape here is a square, and the sides have length of s, and s varies with time, so we're going to have a ds dt. And at a certain instance, the sides are 3 feet long, that's what we put at the end, and the rate of change, that's our ds dt, they're increasing at 2 feet per minute. So what they're asking for is how fast is the area increasing, so they're asking for a dA dt here. So the variables, we have an s for the side of the square, and we have an a for the area of the square. The rates of change, they tell us that the ds dt is 2 feet per minute. And what they're asking for is the rate of change of the area, so dA, the change in area over time, that's our unknown. So draw a picture. All we have to do is draw a square, put an s here, and relating sides to the area, area is equal to side squared for a square. So we take the derivative of that equation. The derivative of a is dA dt. The derivative of s squared is 2s ds dt. And then we substitute in the values that we were given up above. We're trying to find dA dt. So dA dt is equal to 2 times s for sides. Well, it was at the end. We were going to put in the sides are 3 feet long. So 2 times 3 feet. and ds dt is 2 feet per minute. So dA dt, oops, sorry about that. So dA dt is equal to 2 times 3 is 6 times 2 is 12. Feet times feet is square feet per minute. That's the rate of change of area with respect to time. Next one on page 4, we have a rectangle problem here, and we have L is the length of the diagonal. They have this of the rectangle, so that's our shape. So the sides have length x and y. X and y vary with time, so that we have a derivative of dx dt and a dy dt. So x is increasing at a rate of 1/2 foot per second. Y is decreasing at a constant rate of 1/4 foot per second. So we have to pay attention to increasing and decreasing. If it's decreasing, the derivative would be negative. So the variables we have is L is equal to the diagonal, x and y equal the sides of the rectangle. And the rates of change, well, we have a dx dt is equal to 1/2 foot per second. Y is decreasing, so we have a dy dt is equal to negative 1/4 foot per second. And they're asking how fast is the size of the diagonal changing. So they're asking for dl dt. We don't know that. That's what we're going to solve for. So when we draw a picture of our rectangle, we have the diagonal, we'll call that L, we have X, we have Y, and right here we have a right triangle. So the relationship between X, Y, and L is X squared plus Y squared equals L squared. That is our Pythagorean theorem. So when we take the derivative of that equation with respect to time, the derivative of x squared is 2x dx dt plus 2y dy dt is equal to 2l dl dt. And if you want to make this equation a little bit simpler when we're going down to step 5, because there's a 2 that's a common factor in every single term here, we can multiply both sides of this equation by 1/2 to get x dx dt plus y dy dt is equal to L dl dt. And then all we have to do is substitute the values from up above. But the only thing that we don't have right now is L, because they tell us when x equals 3 feet, y equals 4 feet, that's what we put at the end, that's what we put on step 5. So what we're going to do is we're going to draw a little diagram of the x, y, and L. It said x is 3 feet, y is 4 feet, and L we don't know, but we can find it using the Pythagorean theorem. 3 squared plus 4 squared equals L squared. 9 plus 16 equals L squared. 25 equals L squared. So 5 is equal to L. So that 5 is what we're going to put into this equation when we substitute. So the x value they tell us is 3. dx dt from way above is 1/2 foot per second, plus the y value is 4, and the derivative dy dt was negative 1/4 foot per second, is equal to L, which we just figured out was 5, and then dl dt is what we're trying to solve for. So now we just solve for dl dt. 3 times 1/2 is 3/2 feet per second, minus 4 times 1/4 is 1 foot per second, is equal to 5 dl dt. 3/2 minus 1 is 1/2 feet per second, is equal to 5 dl dt. And to get rid of the 5, you can just multiply both sides by 1/5. So in the end, 1/5 times 1/2 is 1/10 feet per second, is equal to the change in the length of the diagonal over time. So there's your answer to partner problem number 1. moving over to partner problem number 2. Now this one is a little bit different because we have an angle here. So we have theta, which is in radians. It's an acute angle in a right triangle. X and Y are the lengths of the sides adjacent to, so X is the adjacent side, Y is the opposite side to angle theta. X and Y vary with time, so we have a dx dt and a dy dt that we'll have down below. So at a certain instant, X equals 2 units. That's what we're going to put at the end on step 5, and is increasing, so dx dt is going to be 1 unit per second, and at the end we're going to put in y equals 2 units, step 5, and is decreasing, so that would be a negative 1/4 unit per second. They want to know how fast theta is changing, so they want to know what d theta dt is. So the variables, what we have is theta, which is our acute angle in a right triangle. We have x, which is the adjacent side. We have y, which is the opposite side to the angle theta. The rates of change, we have dx dt, they tell us, is equal to 1 unit per second. Dy dt, they tell us it's decreasing, so that's negative 1/4 unit per second. And d theta dt is what they're asking for. How fast is theta changing? So what we're going to do now is draw our picture. So we have a right triangle. We have our angle theta here in the corner, and x is the adjacent side, y is the opposite side, and we have an equation that relates theta, x, and y. We can use right triangle trig, SOHCAHTOA. SOHCAHTOA says opposite and adjacent is tangent, so we have the tangent of angle theta is equal to opposite over adjacent. Now when we differentiate that, we have to find the derivative of tangent. Well, the derivative of tangent is secant squared theta, but then we have to tack on d theta dt. When we have y over x, we have to use the quotient rule, and the quotient rule says bottom times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. Now the next thing we're going to have to do is when we substitute in the values, we're going to have to know what the secant of theta is. Well, the secant is the reciprocal of the cosine. And what we're going to have to put in is these things at the end, x equals 2 and y equals 2. So let's draw our little picture here of our right triangle. When x equals 2, y equals 2, and we can do 2 squared plus 2 squared is equal to z squared, if you want to call that z. And when you do the arithmetic, this is just a 45-degree angle, because when the legs are equal to each other, hopefully you know by now that's a 45-degree angle. So 45-degree angles are in relationship of 1 square root of 2. So I know that this is 2 square root of 2, or you can complete the Pythagorean theorem if you want to get that. So if you want to know what the secant of theta is, here's theta down here. Well, the cosine of theta, cosine is adjacent over hypotenuse, so the secant of theta is equal to the hypotenuse over adjacent, which is 2 square root of 2 over 2, and if you reduce that down, the secant of theta is just equal to the square root of 2. We're going to need that value to plug in up here. So let's substitute in secant squared of theta. Well, the secant of theta is the square root of 2. We're going to have to square that. D theta dt is what they want. X is equal to 2. Dy dt is equal to negative 1/4 unit per second. Minus y is equal to 2. And dy dt is equal, or I'm sorry, dx dt is equal to 1 unit per second all over x squared. Well, x is 2. 2 squared is 4. So now all we have to do is a little bit of algebra to solve for d theta dt. Square root of 2 squared is 2. So do 2 d theta dt is equal to 2 times negative 1/4 is negative 1/2 minus 2 all over 4. You can multiply both sides by 1/2 to get rid of that 2 here. So d theta dt is equal to -1/2 minus 2 is -5/2. And then you multiply the 4 times the 2 to get the 8. And then when you simplify that complex fraction down, you get -5/16. And units for rate of change of radians in radians is radians per second. So that's your d theta dt. Number 6, we're going to drop a stone into a pond, sending out a circular. So we have a circle problem. We have a radius that's increasing at a rate, so that's our dr dt of 3 feet per second. And how rapidly is the area increasing? So they're asking for dA dt at the end of 10 seconds. Now this is going to be a little bit interesting because we're going to have to actually calculate what the radius is at the end of 10 seconds in the end. But let's start here. We have variables. We have r is equal to the radius. We have a is equal to the area, similar to the problem we've done before. The rates of change, we know the dr dt is equal to 3 feet per second, and they're asking for dA dt right here. How rapidly is the area increasing? So draw a picture. We have the ripple, we have the radius, we have the area is equal to pi r squared, just like before. When we differentiate this equation, we've done this before, dA dt is equal to pi times 2r dr dt with respect to time. And now when we substitute the values in, remember we're solving for dA dt, we have to know what the radius is, but they don't tell us what the radius is here. They just tell us after 10 seconds. So because the radius is increasing at a rate of 3 feet per second, we can figure out what the radius is. So after 10 seconds, if it's increasing at a rate of 3 feet per second, you multiply those out, the seconds will cancel, and 10 times 3 is 30 feet. So we have 30 feet, which is our radius. So now when we substitute in here, we have dA dt is equal to pi times 2 times the radius, which is 30 feet. And dr dt, they told us, was 3 feet per second. When we do the math, 2 times 30 is 60. 60 times 3 is 180. So dA dt is equal to 180 pi, and it's square feet. Feet times feet is feet squared per second for the units. So that's page 6. Moving on to page 7. We have a ladder leaning against the wall problem. Very typical related rates question. The 13-foot ladder, that is a constant. It doesn't change. At a certain instant, the bottom of the ladder is 2 feet from the wall, so that's what we put it at the end in step 5, and is being pushed towards the wall at a rate, so there's our dx dt, if we want to call it x, at 6 inches per second. And how fast is the acute angle that the ladder is making with the ground increasing? So they're asking for d theta dt for the angle. So what are our variables? Our variables are, well, let's draw a picture first. So we have the wall, we have the 13-foot ladder that doesn't change, and it's being pushed up against the wall, so we'll call this x because this x is changing, and they're asking for the rate of change of this angle right here. This is a right triangle. So we have x, which is the distance from base of ladder to wall. We have theta, which is the angle between ground and wall. And that's it. The rates of change, we are told that dx dt is pushed towards the wall, so that means x is decreasing. If it's going in this direction, it's getting smaller and smaller, so dx dt is going to be negative. And the other thing we should pay attention to is the units. The units are feet here. The ladder is 13 feet, but the rate here is 6 inches per second, so we're going to change 6 inches to 1/2 of a foot. because since they're 12 inches in a foot. So dx dt is negative 1/2 of a foot per second, and what they're asking for is d theta dt. We don't know that. How fast is the acute angle increasing? So we have a picture here, right triangle, and because we have an adjacent side and a hypotenuse, and we can use right triangle trig, we can say the cosine of theta is equal to the adjacent divided by the hypotenuse. And a better way of writing this is 1/13 x, because when we take the derivative, it'll be easier to take the derivative of this rather than in this form. So when we differentiate this equation, the derivative of cosine is negative sine of theta, d theta dt, is equal to the derivative of 1/13 x is 1/13. We have dx dt. And now we substitute in the values. Well, what we don't know is the sine of theta right now, because we're told that this ladder is 2 feet from the wall, and in order to get a sine of theta, we need opposite over hypotenuse. So we're going to draw a little picture down here. When it's 2 feet away from the wall, the ladder is always 13 feet long, and we don't know what this is. We can call this y. Since this is a right triangle, we can say 2 squared plus y squared equals 13 squared, so we can get the sine of theta, and theta is down here. And so this is 4 plus y squared equals 169, so y squared equals 165, so y is equal to the square root of 165. So we can put the square root of 165 in. And now we know what the sine of theta is. The sine of theta opposite over hypotenuse is the square root of 165 over 13, and that's the number that we can substitute in when we do this work. So we have negative sine of theta, which is negative square root of 165 over 13. d theta dt is what we're being asked for, is equal to 1/13, and dx dt is negative 1/2 foot per second. So we've got everything substituted in to this equation, so now we can just do a little bit of arithmetic here to solve for d theta dt. We can multiply both sides by 13 over negative square root of 165. So we can get d theta dt is equal to, this 13 in the numerator and this 13 in the denominator can cancel out. So what we have left in the numerator is just 1, and in the denominator we're just left with 2 times the square root of 165. Negative times negative will give you a positive, so this is a positive. 2 over square root of 165. Now, the feet per second are going to cancel out. We've got the units are going to be in radians per second, because this would be feet, and then when you take the reciprocal of feet, the feet are going to go in the denominator, so that would cancel out with that. So we've got radians per second as our final answer here. So we've got one more problem, and this is about a balloon, a spherical balloon. So spherical means we're working with a sphere this time, our geometric shape. We have a volume that's increasing, so we have a dV dt that is at 3 cubic feet per minute, and they're asking for how fast is the radius, so they're looking for dr dt in this one. When the radius is 1 foot, so that's what we put in the end in step 5, and they're giving us the volume of a sphere. Thank you very much. So what do we have? We have r for the radius of the sphere, we have v for the volume of the sphere. Just 2 variables. The rates of change, they're telling us that the volume is increasing, so we have dV dt is equal to 3 cubic feet per minute, and they're asking for how fast is the radius increasing, so we don't know what dr dt is. That is what's being asked for. So draw a picture of a balloon. Sphere kind of looks like a circle. If you want to put a little string on the end of the balloon, we have r for radius. And what we have to do is relate the variables in step 1, and we're already told that volume is equal to 4/3 pi r cubed. When we take the derivative of this equation, it's dv dt, 4/3 times pi, that's a constant, so we keep that, 4/3 times pi, and the derivative of r cubed is 3r squared dr dt. What we can do here is this 3 in the numerator and this 3 in the denominator can cancel out, so we really have dv dt is equal to 4 times pi times r squared dr dt. And now what we can do is substitute all the values. I think we're given everything here. So dv dt, they tell us 3 cubic feet per minute is equal to 4 times pi times r squared. What did they tell us? R is 1 foot, so 1 foot per minute. No, the radius is, I'm sorry, the radius is just 1 foot. Duh. So 1 foot, but we have to square that, and then dr dt is what we're looking for. So we have 4 times pi times 1 is just 4 pi square feet. So what we can do is divide both sides by 4 pi feet squared. Divide by 4 pi feet squared. And so what we're left with is our dr dt, 3 over 4 pi, and feet cubed over feet squared is just feet per minute. That minute stays, and then we have our answer dr dt, and that is the end of that problem.